Hey folks, so now that we've shot cannons at a bunch of things, it's time to move on to a new module. This one's all about the laws of motions and free body diagrams. The problems we've done so far, a lot of them involve stuff where, let's say I'm accelerating in this direction for this certain amount of time, how far did I travel? Or I launch something and only gravity acts on it, how far did it travel? But in the real world, it doesn't always work that way. There are a lot of things that can happen to me while I'm accelerating. I could get hit by any number of things, and they would all exert a force on me. So what exactly is a force? Well, it's really any push or pull. So if you get smacked in the face by your friend, or soon to be not friend, then that is a force. If you've got a rope tied around your wrist for some reason and someone pulls it because you're a puppet, I guess, that is a pull. That's a force as well. So literally anything that pushes or pulls. And this will cause acceleration. Remember that acceleration could be speeding up, could be slowing down, could be changing direction. Acceleration is any change in velocity. So anytime you've got a force, you've got a change in velocity because you push something in some direction. And force, of course, is a vector because direction matters. I can get hit left, right, up, down, and so on and so forth. So let's dive into Newton's laws. The first one is just that any object in motion will stay in the exact same motion unless it's acted on by an outside force. Or an object at rest will stay at rest unless acted on by an outside force. Basically, another way to say this is the law of inertia. Inertia is just an object's tendency to keep doing what it's doing. So if I have a box and it's just sitting totally still, that is one happy box, and it wants to sit there forever and ever and never have that change. Until I give it a kick, and it's like, no, 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 no. Oh, here, let me draw a kick. I think, okay, so I break my leg, and it slams into a box. And the box is like, no, 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 because I'm pushing it. It doesn't like it. It's accelerating. Then the box starts sliding. And while it's sliding, it's like, hey, this is pretty great. I'm just going to keep moving to the right for forever. And eventually immediately friction acts on it. It slows it down and it stops. But another way of thinking about the law of inertia is essentially this. No force, no acceleration. Which also makes sense. If you imagine the cannons that we were just using to launch all these things, if I fired at, let's say, 3 meters per second, and there was no gravity, it would just keep moving at 3 meters per second in that exact same direction, because why wouldn't it? Nothing is stopping it from doing that. So that's Newton's first law. But that whole no force, no acceleration thing leads actually directly into the second law, that force equals mass times acceleration. Now this right here is essentially the holy grail of physics equations. I guarantee you, every year I have some students come back and they say, yeah, I can't remember all those equations we do, but I remember force equals mass times acceleration, F equals ma. We're going to use that a whole lot. Really, a better way of saying this is that the sum of all the forces on an object equals mass times acceleration. Because you can have two forces acting on you at once, or 3 or 4 or 70 billion. But the sum of all those forces added together, that's a horrific summation sign. Let me see if I can do a better one. Ah, that's pretty. The sum of all the forces acting on an object is its mass times its acceleration. The object's mass and the object's acceleration. So, this only considers forces acting on an object. It doesn't care if that object is hitting anything else along its way. It only cares about the forces acting on the object, not the forces the object is exerting on anything else. When you solve problems involving Newton's second law, you're going to have to break down all your force vectors into x's and y's, just like we did with vector addition. Break vector A into x and y, break vector B into x and y, add up all your x's, add up all your y's, and then bring it back together with the Pythagorean theorem. You'll do something similar with these free body diagram problems. And finally, Newton's third law is that every action has an equal and opposite reaction. So if I hit you, you hit me with the exact same force, but in the opposite direction. A pretty famous problem that physicists like to use is a truck, a big old truck, is heading down the interstate when it smacks into a mosquito. So there's my truck and there's my mosquito. Now at the actual moment of impact, the mosquito technically exerts the exact same amount of force on the truck that the truck exerts on the mosquito. The main difference is the acceleration that both of these things are going to feel. The truck will technically slow down the slightest bit because it's moving to the right, mosquito pushes it to the left, so that causes a deceleration. But it's going to be so very small. Meanwhile, the mosquito that was motionless is soon going to be moving to the right very, very, very fast. So Newton's third law says force on truck equals force on mosquito. And I know that the total net force acting on an object is mass times acceleration. So this could be rewritten with the truck as mass times acceleration equals for the mosquito, mass times acceleration. And it's that acceleration that'll really get you. So the force will, or the truck will basically be undamaged. The mosquito will be very damaged just because of the exact same force acting on both of them. Now, usually there's more than one force acting on an object at a time unless it's in free fall. So here's where these come in handy. They're called free body diagrams. It basically just shows all the forces acting on an object at a certain time, and it allows you to visualize what exactly is going on, which way it's going to accelerate, and all that kind of good stuff. Now, for a lot of the diagrams you draw, I don't care how you do it, I don't care how it looks, I don't care where you put your various arrows. For free body diagrams, these are drawn in a very specific way, and I'll go over that in just a second. But first I want to talk about a list of forces that you're going to encounter most often. Gravity, normal, tension, friction, air resistance, and applied force. So let's start with gravity. A lot of times this is labeled as just Fg, or W for weight, or sometimes you'll see it listed as m times g. Now g is that special constant that you've dealt with over and over and over again, 9.81 meters per second squared. So because force equals mass times acceleration, and the acceleration due to gravity is little g, 9.81, then we'll say the gravitational force is the object's mass times 9.81 meters per second squared. This is going to be present in just about all the free body diagrams you draw. Oh right, I mentioned the object's weight. So weight is a force. In fact, it's just the force of gravity on the object is considered its weight. A lot of times we measure it in pounds. In physics, you're going to measure weight in newtons. Oh, by the way, all forces, I probably should have mentioned this, all forces have units of newtons. And because F equals ma, a newton is simply a kilogram times a meter per second squared. Sometimes you'll see it as kilogram meter per second squared. But that's just a newton of force. So weight, since it is a force, is measured in newtons just like all the others. But mass is not a force, and it remains constant, regardless of location. Even if you don't have a force of gravity acting on you, you still have a mass, but you don't have a weight. Those are the two differences. And mass is measured in kilograms. Another force that you're going to encounter a lot is going to be the normal force. This comes from just being in contact with some surface, and it points perpendicularly away from the surface. So if I'm on a flat, level ground, I'll have gravity acting down, and I'll have normal force acting straight up, because that's what's perpendicular away from the floor. If I'm on a ramp, though, I'll still have whoops, I'm sinking into the ramp. I'll still have gravity straight down, but now my normal force will point perpendicularly away from the ramp. And now we've got x and y components that we need to deal with. Ooh, or if I'm, like, let's say, leaning against a wall, then the force, the normal force would just be pointing directly away from the wall as I do that. So, oh, or I'm poking my head. What am I doing here? I'm leaning against the wall. There we go. Now the normal force here would be this way. So it's always perpendicular, because normal actually means perpendicular. All right, then we've got tension. A lot of times you'll see that labeled Ft, or just T. It's the force in a rope or a string or a cable. It points in the direction of the rope, and it's always a pull on the object. I can't push something with a rope. Have you ever tried like grabbing something attached by a string? You pull it, yeah, the rope gets all taut and then it'll drag behind you. But if you try to push it, the rope will just bunch up and nothing will happen and it'll be really boring. Then there's friction. Friction is caused by the rubbing between two surfaces. And it always opposes the direction of motion, or the way the object's trying to slide. There are a couple of different types of frictions, one where you're not moving yet and it stops you from moving in the first place, one where it slows you down once you're already sliding. And we'll talk about both of these later on in the unit. Then you got air resistance. This is the force of air molecules pushing against things. We ignore these a lot. And then finally, there's just an applied force. Basically, any time you've got something pushing or pulling, sometimes I'll write FAPP for force applied, sometimes FP for force of the push. Honestly, sometimes I'll just write F with a little subscript what it is, force from the slap. The applied force, this is basically the other category. Just look at your situation, and if there's some other force, be sure to include it in your free body diagram. Now, when you actually draw these free body diagrams, all the forces originate from the center of mass of the object, in the drawing at least. Now, once we start getting to more complicated systems, this will be different. You'll have to put the forces exactly where they are acting. But for right now, just treat an object as a simple object with a center of mass. Draw all the forces starting on the center of mass and pointing away from it. They point in the direction they're acting on the object. Which way are they pushing or pulling it? And the free body diagrams only include forces acting in the moment. So if I punt a ball, and we did a free body diagram from the moment my foot came into contact with it, then we'd have gravity acting on it, and the force of the punt acting in the direction that I kick it. But the moment that it lets go of my foot, and it's flying through the air, now it has only gravity acting on it, not the force of the punt, because my foot's not touching it anymore. So don't include any past forces. Sometimes I call these ghost forces, and they do not belong on free body diagrams. All right. So when you're confronted with a free body diagram problem, again, use simpler drawings. A lot of times I simplify boxes down into, or simplify objects down into boxes or just points. Use longer arrows if you know that that force is stronger, and do not include the forces that the object is exerting on something. So, more free body diagrams tips. So basically start with drawing your object, then look at the usual suspects list that I just went through. How many of these forces are active in this scenario, and which way do we point? And I can apply, if I know the magnitudes, I can list those as well. Decide on a coordinate frame, so which way is the y direction pointing, which way is x pointing. Break everything into x's and y's. Add up your x's, add up your y's, and you've done it. So once again, here's the usual suspects list. All right. I think I've already gone through all this, so you know what you need to know about that. Finally, once you've got the net force acting on an object, the sum of all those force vectors, it's mass times acceleration. And we'll go through a bunch of examples of this in class. Right. Now there are a couple of cases. One is equilibrium. Either an object is not moving, or an object is moving with a constant velocity. In both those cases, the object's acceleration is 0, and through F equals ma, well, mass times 0 is just 0. So in this case, the sum of all the forces will be 0. If the object is accelerating, F equals ma. Always remember that. So we'll talk more about that in class. See you then.